Hello and welcome to this webinar, Modern Open Source Approaches to Software for Automation Systems, Eclipse Arrowhead and Eclipse 4diac. Thank you very much for joining. Some housekeeping first. Your microphones are muted. Please keep it that way. Of course, please also feel free to type your questions into the chat. So there is a Zoom chat window that you should see in your client anytime, and we'll come back to them after the presentation. Then there is also going to be an opportunity for you, provided that we can manage, given the number of participants, to talk to us, of course. The slides will be made available on the MIDIH website, and this presentation is also going to be recorded, but we will not make your questions public because we want you to be fully open with all your questions. This webinar is brought to you as a joint effort between Luleå University of Technology in Sweden, Fortis from Munich, Germany, and the Polytechnic University of Milan in Italy. Therefore, we have speakers and experts from all three organizations with us today. I think it's time for a brief round of introductions. Jerker, may I ask you to start?
Yes, Jerker Dosing, professor at the Luleå University of Technology and one of the primary architects behind the Eclipse Arrowhead framework.
Hello, everybody. My name is Sandeep. I'm also working at Luleå University of Technology. I'm a senior lecturer here at the university.
Hi, I'm Marco, and I'm a master student at LTU University.
My name is Georg Neugschwandner. I'm with Fortis, the Research and Transfer Institute for Software-Intensive Systems and Services of the Free State of Bavaria, where I'm with the SME support team.
Good morning, everybody. I am Simone Galparoli, and I am a researcher at Polytechnic University of Milan, where I work in the Industry 4.0 lab.
Thank you very much. So Sandeep will now introduce the two frameworks. Marco will show how they are brought together from a software engineering point of view, and I will then introduce our joint use case in the lab in Milan. But first, we would like to get to know you a little. How familiar are you already with the topics that we're presenting today? You should see a questionnaire appear on your screen right now, and this is going to be an anonymous poll, of course. So please give us a bit of information. Who is with us today? The size of your company is, of course, relevant for us since the MIDIH project wants to support small and medium enterprises in particular. So we're interested how many of these we are reaching. Okay, so we have 35 participants, and a bit more than half of them have already provided us with information. Okay, so not many are familiar with the MIDIH project, but we have many participants who are already familiar with either the Arrowhead or the 4diac framework. All right. Thank you very much. I still see some answers coming in, but I think we have most of your feedback right now. Okay, so we do have many participants who are familiar with either Arrowhead or 4diac, but we don't have many who have already heard of the MIDIH project. So allow me to briefly introduce this project, which has also enabled this webinar. MIDIH stands for Manufacturing Industry Digital Innovation Hubs. And it is a European project with 21 companies and institutes participating. The goal of this project is to improve the support that manufacturing enterprises get for going digital, and small and medium enterprises in particular, as I've already said. Therefore, this project is also part of the European I4MS, that's short for ICT Innovation for Manufacturing SMEs initiative. And the approach of the MIDI project follows two main angles in order to reach its goal to improve the support for SMEs to go digital. First, it strives to enable better collaboration between digital innovation hubs and knowledge providers by supplying an organizational framework, methodologies, and a digital platform. But second, the project also aims to offer guidance in applying open source software. And this angle is very relevant for us today. For this purpose, a reference architecture was developed in the MIDI project. And the basic idea behind it is just to say, if you want to create data-driven applications, so either for smart products, for smart manufacturing, or to support your supply chain, these are open source software components that you could use. And on this slide in particular, to the right, you see the components that are suggested for smart factory and smart product applications. They are based on the FibeAir and Apache data technology stacks, but the architecture also includes complementary items to make the picture complete. And Arrowhead and IC64099 are two of them. Arrowhead complements the technology stack as a new paradigm for connecting automation software components, and IC64099, the standard that the 4diac framework is based on, complements the stack as a framework for implementing distributed automation software components. So mainly connecting on one hand, mainly, not only of course, implementing on the other hand. And today, this webinar is about how these two work together. So Sandeep, please give us a bit of introduction on Arrowhead.
Thank you, John. Arrowhead, Eclipse Arrowhead project began in 2003 and has been growing ever since. Today, Arrowhead refers to a set of principles and tools to design and implement service-oriented architecture-based systems, especially in the Internet of Things area. It focuses on many different areas, such as production of goods and services, smart buildings, electromobility, energy domain, etc. And how does Arrowhead does this is by creating local clouds. So this is one of the artifacts of Arrowhead, and it starts off, the Arrowhead local cloud provides mainly the core services. We will come to these core services soon, what they are. And then you can add on to these systems. You can develop your own application systems, sub-applications that interact with each other using these core services. And it uses a simple producer-consumer methodology for information exchange. So why do we need to use Arrowhead, or where you can use Arrowhead? Arrowhead is being used to address mainly interoperability between IoT components and also building system of systems from each of these individual IoT components. The main emphasis is on real-time system properties, high level of device system and network security, and very ease of engineering within these automation systems. Now, if you want to get started with Arrowhead, what you can do, you start off by abstracting your IoT things or into functionalities into services. And this will enable loose coupling data exchange between the producer and consumer systems. Then you create Arrowhead local clouds. And to do that, the framework provides the integration platform, the engineering processes, tool chains, and tools. And then optionally, you can do a Arrowhead compliance check that's coming soon to the Arrowhead framework. So what does the framework consist of? The framework consists of many different things, providing systems, functionality for the whole ecosystem of automation system, starting with core services. These are authorization, service registry, and orchestration. Registry includes the capability of registering and discovering of services within the local cloud. Authorization and authentication is for service exchanges between the producer and consumers, so that you know that the right consumer is and the right producer is involved in this information exchange. And then orchestration of service exchanges between the producer and consumers. That is, you can orchestrate the system of systems. And when you start using Arrowhead into your own system and you need a service, there's a good possibility that it exists. And you can check before you develop your own services. For example, one of the things that we'll see later today is called Data Manager. And Data Manager system is used for storage, processing, and visualization of large amounts of data, mainly sensor data. And in our case, the use case that we're going to show soon, there was a need to use this stored sensory data. And of course, you have interoperability plugins, such as the ones for 64099. And that's, again, something we're going to look at today. So with that, I now come to the other part of it, the Eclipse 4diac. Eclipse 4diac provides an open source infrastructure for distributed industrial process measurement and control systems. And this is based on the IEC 61499 standard. It's a cross-platform IDE, and runtime is available for many different hardware platforms. It has an IDE where you develop your systems, a top-down approach, Forte runtime, like I said, supporting many different hardware architectures, comes with function block library and some example projects. IEC 61499 is an international standard describing a reference architecture for distributed automation systems. In that, it substantially differs from the popular 61131 standard that describes a set of programming languages for PLC programming. Informally, the standard is known for using a component-based model similar to block diagrams. This is why sometimes this standard is also referred to as the function blocks standard. Typically, when you develop 64099 application, it would look something like this, that is made of many different function blocks. And there are different kinds of these function blocks. And some of the three main types of function blocks are a basic function block, a composite function block, and service interface function block. A basic function blocks consist of the main atomic unit where the actual execution of logic happens. So that's why this block consists of a state machine that defines the state transition logic for your function block, and also the algorithms that will be executed in each of the state. The composite function block itself is made up of no such state machine or algorithms, but it is composed of other function blocks. It can be basic function block, it can be service interface function block, or it can be some other composite function block itself. And then for things that are hardware dependent or specific to particular hardware, you write something called service interface function blocks that are specifically meant to run on specific hardware only. So why do we use this? The key word in the standard is distributed. The term distributed automation has been subsequently applied to 3 generations of technology. The first generation was distributed sensor data acquisition or use of these sensor data, which are geographically spread out. But then the processing is still happening on a centralized PC. This is referred to as a PLC. Then came a concept of remote IOs, wherein architectures such as Modbus and Profinet were introduced, which meant there was still a centralized PC, the PLC, which was connected to the remote IOs using architectures such as Modbus and Profinet. So that was what is currently often referred to as the distributed control system. And then now today, we come to 6.14.99, where it's truly distributed automation systems. That means there is an absence of centralized processing. So the idea is that there has to be some intelligence at the very end where these IOs are actually present. So it is different to the other standard in the terms that it's deterministic. It's open standard, helps with portability. It has an open function block model. You can enable encapsulation, thereby enabling reusability. It's an open device management mechanism, helps with configurability, provides service interface function blocks to encapsulate hardware-specific functionality, and then finally compliance profile enables interoperability. So 6.14.99 systems, when it is running in your automation system, your hardware necessarily does not have to be from the same vendor, for example. In summary, it's an event-driven approach. That means it's not scan-based cycle like in 6.11.31, and only when there's a specific event that occurs, the function block is executed, not every so many milliseconds. More powerful abstraction than 6.11.31. It has a better support for distributed control. All you have to do is select in your application which function blocks runs on which hardware. That's it. You do this mapping and the rest is taken care by the runtime system. Better software maintainability and reusability, of course. Now I hand over to Marco, who will present the use case.
Okay. Let me start by introducing the use case and then explaining how Arrowhead and 4diac communicate together. It is composed by 2 conveyor belts driven by 2 IceBlock Necro PLC controllers, and there are sensors to detect the position of an object on the beginning and the end of each belt. After the presentation, you can find a video of a test on the link below. What we want to achieve is these 2 controllers talk to each other via one of the many services that Arrowhead provides, as you saw in the slide that Sandeep presented. We will specifically use Arrowhead Data Manager. If you are wondering what IceBlock is, it is a wireless PLC, currently Wi-Fi, with support for 5G coming later this year. It has 4 digital inputs and 4 digital outputs. And it has a chipset very similar to BeagleBone Black. It supports 4diac fault runtime. And here is the state machine that controls the conveyor. When the system is turned on, the ECC of the controllers will move to an initialization state, and the IceBlocks will initialize the variable last inside the data manager to 0. After that, they move into a waiting state. And for example, if an object is put on the 4th sensor of the conveyor related to IceBlock 103, then its ECC state moves to state 2, and the belt starts moving in the direction of the second belt. When the object reaches the second sensor, ECC of IceBlock 103 moves to state 3, and the IceBlock updates the variable last inside the data manager. While IceBlock 101 reads the updated value of last from Arrowhead, it makes move the second belt, so that the object can pass from the first conveyor to the second. Belt related to IceBlock 103 will move until the object reaches the fourth sensor of the second conveyor, and at that moment it will update the value of variable last inside the data manager. The second conveyor will stop when the object reaches the end of it. After that, the object will move back to the beginning of the first conveyor belt in a specular way, and then it repeats again the same movements. Here is the network configuration for the use case. The two IceBlock PLC are running 4diac Forte, and a laptop is running the Arrowhead services. All the devices are wirelessly connected to a router. The Arrowhead data manager allows the controllers to share their sensor state and the program variables. We designed and developed following function blocks to talk to Arrowhead data manager. The communication function block, and using that function block has been created the send type to data manager and the output historian type. We will take a look at these blocks and what they do soon. This is the developed 4diac system. It is composed by the pink part of the application running on IceBlock 103 and the blue part of the application running on IceBlock 101. Here you can see an example of the data format that is sent and received to and from the data manager. The most important are the service name, the current time, and the data. It is important to attach the current time to the data because the variable can be updated only if the new time is greater than the stored one. Now, let's take a look at individual blocks. The highlighted function blocks are used to write and read from and to the IceBlock inputs and output. To use these function blocks, it is necessary to activate the write module when compiling Forte. And you can find this information on the 4diac website. The send type to data manager and the output historian type are function blocks that allow the communication with Arrowhead, specifically the data manager. In particular, the output historian type is used to get information about the variable last and about one of the other sensor of the other conveyor belt, while the send type to data manager is used to update the variable last and the sensor status needed from the other belt in Arrowhead. Finally, the main control block, which is used to move an object from the beginning of one conveyor belt to the end of the second one, and back to the beginning of the first belt. This state machine we saw a few slides ago is part of this function block. Each controller function blocks take as input the value of the sensor of the related conveyor, the value of the closest sensor of the other belt, and the variable last that stores the last activated sensor. Instead, as output, they have the variables used to move a belt forth and back, and the variable used to update the value of last when necessary. At the moment, 4diac has libraries that allow Forte to communicate with Arrowhead 4.1.2. More in detail, it is possible to communicate with the service registry, the orchestrator, the authorization, and the event handler core systems. For the last version of Arrowhead, it is possible only to communicate with Data Manager at the moment. The Data Manager is a new version is new in version 4.1.3 and was not yet available on the version 4.1.2.
Thank you very much, Marco. So now that you all have seen how to access the Arrowhead local cloud from within a 4diac application, we thought it would be interesting for you to see a use case involving industrial equipment. And for this purpose, Fortis and LTU have joined forces with the Politecnico di Milano Industry 4.0 lab, which is one of the didactic factories in the MIDI project. And part of their equipment is a fastodidactic CP factory assembly line, which includes a robotic assembly cell. So that's exactly what you see in the picture here. Among other things, this robot, which you can see inside the housing here, places fuses onto a circuit board. And these circuit boards come out of a supply crate, which is loaded into the cell from the back of this housing that you see here. When the supply crate is empty, a conveyor moves it to the loading position that you now see marked with this red oval here to be refilled. Now, someone would usually have to take the empty crate to a storage area to refill it, but the lab has also an AGV, which is controlled by fleet management software that was developed in another I4MS project, which was called L4MS, Logistics for Manufacturing SMEs. And what we want to add here is a 4diac PLC that monitors the sensors on the conveyor belt that are already present there, that detects when the supply crate needs to be replaced and automatically calls the AGV through the existing software infrastructure. In addition, the PLC will also monitor the time that it takes for the crate to actually be replaced. Now, how can we make good use of this information, of this data? Now a second aspect of the lab comes into play. It also has a digital twin of its assembly line. And this digital twin was actually created also within the scope of MIDI, more precisely in one of the MIDI open call experiments by the Italian company TTS. So what this means is that this company applied to an open call for experiments within the MIDI project with their idea. There were 2 of these calls. Their proposal convinced the independent reviewers, and then TTS received funding on one hand and technical support on the other hand by LTU and Politecnico di Milano to implement their idea. And what was their idea? A simulation model of the assembly line that receives essential parameter values directly from the actual assembly line, so from the hardware, using the MIDI integrated architecture. And in this case, the part that was used from the MIDI integrated architecture was the Arrowhead local cloud. So information from the PLCs on the assembly line is provided to the Arrowhead local cloud, and the MID3, that's the name of this experiment, that this MID project within the project, the MID3 management module receives these notifications through the Arrowhead local cloud and determines from them how long certain actions take in the real world. This enables the simulation engine to then use these time measurements for a more realistic simulation. So what we want to do here is to take the new time measurements, how long it takes for the crate to be replaced after the EGV has been called, the time measurement provided by our 4diac PLC, and supply it through the Arrowhead framework to offer it to the simulation. And this is how all the components will play together. The PLC uses 4diac to run an IC64099 application that monitors the sensors which are connected to its digital inputs. The PLC has an integrated OPC UA server that it will use to expose this information that a new full crate with circuit boards is needed. And this information is then picked up by the existing 5-ware-based infrastructure that was created in the L4MS project. And by the way, here we'll be using another piece of software that was developed in the context of MIDI by the company Engineering, which is an OPC UA client for the 5-ware IoT agent framework. But the second information path in this big picture, which is of course the one which is relevant for our topic today, is that the 4diac application also has an Arrowhead client on board that it uses to offer our time measurement through the Arrowhead framework local cloud to the digital twin. And the IC64099 application in the 4diac PLC actually looks very similar to what you have already seen on the previous slides. So it uses the IX function blocks to access the digital inputs. It uses some basic function blocks to implement the logic with a state machine represented as an execution control chart. And it uses service interface function blocks for the communication services. So we're right now in the process of prototyping this. Unfortunately, the health situation has made us run a little later with this than we had initially hoped. But anyway, especially given this situation, it's very convenient that the IC64099 application is hardware independent and that 4diac supports multiple hardware platforms. So this means that we can test everything on a Raspberry Pi, and then when everything works, we deploy the same application on an industrial PLC. And basically the only thing that we need to change for this is the pin number on the params input of the IX function block. And of course, what we're showing with all this is that a seamless integration of PLCs into service-oriented architectures is possible. And of course, service-oriented architectures allow making system components more independent from each other, to decouple them along clearly defined interfaces. And this in turn means that it becomes easier to manage the overall complexity of the system and maintain it over its lifetime. Where maintaining, of course, means adding or modifying functionality, just as the time management, this new time measurement that we were adding in our example here. So, in summary, today we have introduced the MIDI integrated architecture for building data-driven smart factory, smart product, and smart supply chain applications based on open source software to you. We have seen two approaches to better maintainability, reusability, and flexibility of distributed automation software, namely service orientation and IC64099. We've seen two open source frameworks that implement these approaches, Eclipse Arrowhead and Eclipse 4diac. We've seen how IC64099 applications that communicate through the Arrowhead local cloud look like, and we have seen an application example involving industrial equipment. If you would now like to learn more about IC64099, there are a couple of books we can recommend. Going from left to right, this would be one book that we recommend for designing and modeling 64099 systems. So a good first conceptual introduction. The book in the middle follows really a hands-on approach to 64099 systems and is going to guide you through developing a complete application from scratch. And if you really want to look into the internals of an IC64099 runtime, then the book on the right would be for you. But if you don't have the time to read an entire book right now, we can recommend a much shorter video tutorial, which you can very quickly find on YouTube. It's not the only one that is out there. The others are also good, but that would be one of those that I recommend starting with. And for Arrowhead, the best and most comprehensive reference is the book IoT Automation, Arrowhead Framework by Jelka Delsing, who is also with us on the call today. So this concludes our presentation. Thank you very, very much for your interest, for joining us, and for your attention. Of course, we'll be happy to hear from you. So please feel free to also, after the webinar, contact us with all your questions and suggestions. We left our contact addresses here for you, and we will have also time for some questions right away. But before this, we would like to ask you for your opinion on our webinar. So there is a second poll, and you should see the second poll right now. So basically, we're really interested how well we did in explaining the purpose of what we showed you today, if we met your expectations, and of course, if you want to give us open feedback, no matter if positive or negative, which is outside the tight frame of this poll, we would also be very interested in that. You can either simply type it into the chat, or if you prefer to leave this feedback to us anonymously, please use the link that we've provided on the slide here. I'm also going to copy it into the chat for your reference and for easier linking in a second. Okay, we are going to leave the poll window open. We hope it doesn't stay in your face too much for anyone who still wants to fill in the questionnaire at a later time. Thank you very much for your feedback already. And now it's time for your questions and hopefully the answers that we can give.